Okay? Now, part 7, differential operator. See? Lecture 8, the Laplacian of a scalar function. Okay? This is phi is a function of x1, x2, and x3 in the non-conservative form. Now, attention now, okay, what I said. You see, these are generalized coordinates, extrinsic geometry, 3 dimension. Okay? Today is March 26, 2025. So, you see, don't forget about the nabla operator in the non-conservative form. Okay? You see, this is nabla operator. Okay? This is nabla operator. You see, divergence of a gradient, okay, is the Laplacian, okay, of, in this case, of the function phi. Could be Laplacian of a vector, okay, which is a first order tensor, okay. Phi is a scalar, okay, is 0th order tensor. Don't forget that. Now, you see this derivative over here, we can expand. See? Don't forget this dot product here, okay? This dot product here, okay? Now, you see, I'm just working on this term over here. Partial Ci, Aj, partial phi with respect to Cj. So I use the Leibniz rule, okay? The product, because Aj is a variable, and this partial derivative here is also variable. So I can expand, just straightforward. Then I can group Ai. Now I substitute this right here. So I have to take the dot product of Ai dot this result over here. Okay, I just set over there. Now remember, always remember, we demonstrated that the partial derivative of the contravariant basis with respect to I is minus, this is gamma ikj ak. We did this many times. So I will substitute this, okay, right here, okay, on this term over there. So this is minus gamma ikj partial phi. Now ai dot ak. You see, ai is a dot product between ai and now ak. Ak comes from here. Plus ai dot aj. Now, this is a second derivative over here, okay? You see, you take the derivative of the derivative, okay? That's a second derivative. Now, you see clearly that this expression for the Laplacian, I just plug this term over here and this term over there. Okay, don't forget to see, it's important here, Gij is ai dot aj, okay? Contravariant, these are the metric components, the contravariant metric components. So, this is Gik because ai dot ak, this is Gij because ai dot aj. Contravariant basis. Attention now, okay? Ai aj contravariant belongs to the dual vector. Okay, this is a dual vector in this case. So that's it. Now I use the property of the metric. You see, we derived this GMNAM. Okay, I looked here, okay, and I substitute for the up. This is the upper index. Likewise, the same here, there's a property. So I can look here, you see, GIK, I choose, okay? I will eliminate K and set I, or eliminate I, set K, doesn't matter, you see? Because KK or II are dummy, no problem. So I substitute, I just get this term over here, see it, gamma J, now here, II, okay, just from this minus term over here, okay, this will be II. And the second one, I just repeat, so it's there. So this is the Laplacian of the scalar function. Could be temperature, mass, specific mass, density mass, no problem. You see, this must be a scalar, okay? That expression, attention now, extrinsic geometry, okay? This is a generalized coordinate, you see? That, so this part over here is good always for you to remember, to recall this important relation over here. Okay, that's Laplacian of the scalar in generalized coordinates. And don't forget, you see, in this case, you have in this case, AJ cross AK is AI, divided by square root of G, okay? This is AI, the contravariant basis that belongs to the dual vector or covector space, okay?